Ladies and gentlemen, we are going to we are going to look into the third part, that is the material that is used in aluminum casting industry. To start with, let me share my screen with you. Oh, okay. Here I am thinking of discussing some of my experiences and some of my views and opinions and knowledge about this whole aspects of aluminium. There are two major portion to my presentation today. One is introduction to pure aluminium. What is aluminium? And the second part is the alloying elements and their effects in aluminium cast alloys. Gentlemen, aluminum is okay. Ladies and gentlemen, aluminum is the metallic element. See, you all know that all the elements are parted in two ways. One is metal and the other is non-metal. Here we are talking aluminum. Basically, it's a metal. Atomic number 13, very highly reactive. Chemically, it is very highly reactive. Therefore, it is not found uh, free in nature. It's always available in the form of compounds and oxides and hydroxides. It is never found free aluminum like gold or other metals. Found combined over 270 different minerals. And gentlemen, this is produced in the year 1820. It was discovered. It's roughly about 200 years old. And one of the youngest metal. Source of nearly 99% of metallic aluminum is bauxite. It's a mixture of similar minerals that contain hydroxides. 1 minute. How much aluminum is on Earth? This is just for your information. Roughly in the core of the Earth, there is 32% is iron. That is right in the core of the Earth. And some amount of iron is available in the surface. Oxygen, silicon 5%, magnesium about 13%, sulfur 3%, nickel 1.8, calcium 1.5, and aluminum is 1.4%. This aluminum in the crust, this outer surface, is about 8%. These are the major countries which is producing bauxite from which we extract aluminium. Australia, about 40% of the world available ore content. Brazil, Jamaica, India, and Russia. So India is one of the top 5 for bauxite reserves. You all know that aluminum was originally extracted and reduced to metallic aluminum in 1820 by chemical reduction process, which was very expensive. In the early stages, aluminum was more expensive than silver. Okay, then later this process came Hall Herold cell process. There are two scientists, Hall and Herold. They produced this electrolytic process. They discovered this method by which the extraction of aluminum becomes extremely easy and fast, and the cost of metal also came down drastically. Uh, when you are smelting aluminum, it's highly energy intensive process. Roughly about 18.5 kilowatt hour. That's about 18 units per kg of metal produced from the bauxite. Abundant hydroelectric power source is needed. Worldwide, roughly about 65,000 metric tons are produced in the year 2021, and projected is about 70,000 metric tons in the year 24-25. Aluminium is very versatile material. It can be cast, forged, extruded, rolled, drawn, welded, machined, heat treated, vapor deposited, electrode deposited, chemically colored, painted, etc. etc. Very versatile metal. can be recycled indefinitely. This is the most advantageous part of the basic metal without loss of properties. See, when you are remelting it and refining it, recycling it, the original property is not get lost. 85% of normally from the scrap we can recover 85% economically, and again recovery or recycling costs only 5% of the original power required to produce a fresh aluminum from the bauxite. Aluminum is the fastest growing metal in the world in the last 50 years. Growth of steel in the last 50 years is roughly about 4 times, whereas aluminum is about 13 times more. Aluminum can be recycled indefinitely. Nearly 70% of the aluminum ever produced, I believe, still to be in use the last 50 or so years and more. Recycling uses only 5% of the energy. Caution. Aluminum, though it is very advantageous with all the plus points, aluminum is the most unforgiving metal. If not treated with due respect and care at every stage of manufacturing, it will extract a heavy penalty. Process control parameters are not to be trifled with. Uses of aluminum. You are all familiar. Electrical industry worldwide as well as in India, it consumes most of the aluminum, roughly about 41%. Transport 17%, which includes people like us who are in the casting industry. Consumer durables 7%. Building and architecture about 14%. Packaging 5%. Industrial machinery 8%, and other applications 8%. Present status of die casting industry in India. This gives you a very rough idea of where all aluminum die castings are used in India. Uses by sector. Automotive sector uses about 70% of the castings produced. Domestic appliance 5%, hand tool 5%, pumps and motors 8%, textile machinery 3%, and others about 9%. These are some of the castings used in automobiles, just to give an idea. Okay, these are the historical aluminum content in cars, So we major consumer for die casting industry is automobile, and again most of them go into cars and two-wheelers, motorbikes, etc. Roughly in 1990, 50 kg of aluminum components and castings were used in cars. Today it's about 180, 230, 2030, I don't know. It's going to be much, much, much more. Already we have exceeded roughly about 200 kg of aluminum components per car. I believe Tesla is producing even the body with the aluminum sheets and castings. Now, this is just to give an idea of what's happening in a die casting foundry. Energy use, this is most important. This I took it out from some other data. Melting consumes about 55% of the entire energy used inside the foundry. When I say energy, it is inclusive of oil, diesel, electricity, power, everything put together. Melting normally consumes about 55%. Holding is about 22%. Die casting or the casting process about 11%. Trimming, fettling, etc. is about 3%. The other non-process office, etc. consumes about 9% in general die casting industry. Now let's come back to pure aluminum. When you say pure aluminum, it's about 99.5% to 99.8% pure by weight. Density, you all know, it's 2.7 grams per cc. Pure aluminum melting point is about 660 degrees centigrade. The material is very soft. Pure aluminum is very soft and malleable. Ideal for wire drawing and making very thin foils. Aluminum foils are extensively used in packaging industry. Major uses: electric wires, foils, and sheets. This is the pure aluminum. There are also, one second, yeah. There are some castings are also made on pure aluminum. I'll come to that slightly later. Melting point comparison. This just to give an idea. Aluminum melts at 660 degrees centigrade. Cast iron at 1350. Boron 2300. Silicon 1440. Copper 1083. Magnesium 650. Manganese 1240. And titanium 1315. Pouring temperature again same. We are comparing the density. Aluminum is 2.7, roughly one third of iron. That gives a major advantage over steel and iron. Boron is 2.3 and copper is 8.96. So copper is also much heavier metal. Magnesium is of course lighter, 1.74. When you make an alloy will have some of these elements into the aluminum, so the density will go up. For example, if you add silicon, let's say aluminum copper alloy, the density will be slightly higher. Aluminum silicon alloy, slightly lower. Depending on the percentage by weight you add in any given alloy, the density will vary marginally. Pure aluminum, very low fluidity, very difficult to cast. Very difficult to cast in gravity die casting, to some extent possible in sand casting. Suitable process is centrifugal casting for rotors. And again, pressure die casting, in some special process, rotors, pure aluminum is used. I have been to a foundry where they produce rotors by PDC. Aluminum also has got a very high affinity for iron. It's highly reactive, as I told you earlier, and it has got a high affinity for iron. Tendency to stick to steel die is very high. This point again will come back slightly later. Now, gentlemen, having spoken a little bit about pure aluminum, I'm coming to the main part, the alloying elements and their effect. This is our main subject for this today's program. What is an alloy? Alloy is nothing but a homogeneous mixture of two or more metals and elements. I say element, I'll come to that later. Two or more. It should be a homogeneous mixture. In the molten state, it should be thoroughly mixed. Properties of alloy differ from alloying elements. You see, you take a glass of water, add a little bit of salt, right? Water has got a different properties. Salt has got a different property, but the salt solution, what you produce, has got a slightly different properties. Something comes from water, something comes from the salt. Same thing happens in the aluminum alloy also. When you make an alloy of aluminum, let us say with silicon or copper, it takes some properties from silicon, and major properties of aluminum is retained, and it forms a third, what do you call, a metal, a property with slightly differing property. Properties depend on the proportion of the metal. Suppose you are adding 3 or 4 metal to aluminum, it extracts different properties proportional to the percentage added. Now, there are two things are there in alloys. One is that major alloying element, the other is minor. When I say major, the proportion is much more than 1%, up to 20-25%. Silicon, copper, magnesium. These are all major alloying components. Minor elements are iron, manganese, nickel, zinc, lead, tin, and titanium. We also add a little bit of strontium, etc. I will come to that slightly later. Some of the minor elements add to a fantastic improvement in the property of the alloy. Gentlemen, unless we take care of the alloy, if you have a very good alloy, the properly manufactured, properly made alloy, one third of your shop floor problems will get solved on its own. Molten metal, the aluminum alloy, is extremely important in the casting operation. Now, aluminum silicon. Now, you all know silicon is the major alloying element. May vary from 0.3% to over 25%. Silicon improves fluidity and improves the feeding in the castings. Increases the hardness. Silicon is a hard material. By the way, this again I wanted to mention a little bit here. Silicon is a non-metal. It is not a metal. When they discovered silicon, they thought it's a metal. The scientists in that time, that period. So they named it a silicium, like aluminium. All the metal in Latin name, it ends with um. So same way they named it silicium. Later they made it silicon because it's no longer classified as a metal. Though silicon is not classified as a metal now. Like graphite or carbon is added to iron and steel. Silicon is here added to aluminium to improve the hardness.
At the moment, I don't have the information
to improve the mechanical strength and other properties, castability, machinability, and all. When you add silicon, it also reduces the electrical conductivity. It has got a very big influence on freezing temperatures. Pure aluminum freezes at a particular temperature, whereas aluminum, when silicon is added, the freezing temperature makes a change, differs a little bit. Silicon has the most favorable influence in comparison to all additional elements. We have aluminum, copper, silicon, magnesium in the major alloying components. Silicon is the most favorable influence and very widely used. Aluminum silicon alloys are very widely used. Probably more than 80-85% of all the alloys are used in casting industry is aluminum silicon. Silicon is always present. There are very few alloys where silicon is totally absent, like LM11, aluminum copper. Okay, coming back to aluminum silicon alloy, solidification shrinkage is only 3% for eutectic composition versus 6% of pure aluminum. Solidification contraction is about 6%. Whereas when you add silicon and make an alloy, the solidification contraction is 3%. That means it is easy to cast, especially in gravity and low pressure. Silicon addition improves the grinding and polishing properties. This is again more. Nowadays the castings needs to be finished with after proper machining and all. So the silicon to a great extent improves the hardness and improves the grinding and polishing property. Ionic oxidation further increases corrosion and wear resistance. Wherever you expect a corrosive atmosphere and where there is going to be a requirement for wear resistance, silicon is your main alloying element. I'm just giving a phase diagram. Here there is, you can see, eutectic point is about 12.6 it is shown. Actually there is a lot of discussion in this point. Many papers indicate it is 11.7. Okay, so the eutectic point is the lowest point at which liquid can survive, and again it becomes solid immediately 1 degree below, that is 577. This eutectic point is the point at which the liquid becomes solid directly. So if you have an eutectic alloy, we call it a short range freezing alloy, where the shrinkage is also low, the casting shrinkage, and also it becomes solid directly. These are the basic major aluminum silicon alloys. One is low silicon alloy LM4, where the silicon is 4 to 6%, medium is about 8 to 10, 7.5 to 9.5, LM25, AC4C, very widely used. And then eutectic alloy 10 to 13%. Again, this is very widely used, LM6 and LM24, etc. They have 10 to 13% silicon. This 10 to 13% also I'll come to you little bit later. I would always suggest that we should keep the silicon below 12. I would always suggest that silicon should be maintained below 12. I'll again come back to that reason later. There are some silicon alloys which is using more than 16% piston alloys. Now, we are talking about eutectic point. Here I mentioned 11.7. Many papers indicate that this percentage is eutectic point or eutectic silicon content is about 12. So we normally go by this 11.7%. Eutectic temperature is 577 degrees centigrade. Also the lowest point at which alloy is in the molten condition. Eutectic alloy properties. LM6 or LM24 is widely used in casting industry. It has got a very short freezing range. When I say short freezing range, it freezes within a very small range of temperature. When you pour the metal into a die or when you inject the metal into the die, it starts cooling down. It starts losing the heat. The temperatures get slowly drops. The alloy which freezes in a very short range, it gives a very good what you call a casting quality, very less shrinkage and also dispersed shrinkage. Solidify with the primary shrinkage, good for thin castings. Since the fluidity is extremely high, you can go for a very thin casting. LM6, LM9. LM9 is more or less like LM6. LM9 also has got certain small quantity of magnesium. Sometimes they add copper also. LM13, yes, we add a little bit nickel here, and LM20. Now, when you classify aluminum silicon alloys, we normally classify into three categories: hypo, hyper, and eutectic alloys. Eutectic is the point, 11.7%. Below 11.7%, we call it hypo, and above is called hyper. Any alloy which is less than 10%, we call it hypoeutectic alloy. They are not necessarily short range. They are having a long range of freezing. Therefore, these alloys, when you are handling it, you have to provide a sufficient in gravity and low pressure. You have to provide a sufficient head. A good riser is required. And in pressure die casting, you go for a very rapid cooling. Hypereutectic alloy is about 13%. Here I wanted to discuss the point which I was referring a little bit earlier also. Normally we talk about whenever you make aluminum alloy, we talk about 11.712. I have seen many die casting industry insist on silicon around 12 or 12 to 12.5%. I am not in agreement with this view. I'll tell you why. Silicon is a difficult element to dissolve in aluminum. You take a glass of water, you add salt, you stir slightly, stir slowly. Water is the solution or a solvent. Salt, the sodium chloride or a kadi namak, which you are adding, is the salt. It goes into solution. When the entire salt has gone into solution, you can't visually see the salt particles. Likewise in aluminum also, when the aluminum is in the molten condition, it's in the liquid state, let us say 750 degree to 800 degrees centigrade. Silicon dissolves easily above 800 degrees centigrade. Your alloy maker has to maintain a temperature 800 degree plus on the molten metal and add silicon lumps. Now what happens here, and he has to slowly stir the metal, the silicon goes into solution. It dissolves like salt going into water. The silicon goes into molten metal. This is very critical. If the alloy maker does not provide sufficient time for the silicon to go into solution fully, the microstructure of the ingots which is produced will have a very coarse silicon particles. Normally we expect a needle-like structure or better a globular structure of silicon. This is very important. Many foundries don't even check the incoming material. We check only for the chemical composition. We don't check the microstructure. It is important that we should look into the microstructure, whether the alloy maker has added the silicon properly, whether the silicon has gone into digestion properly. This is very important, because this is going to make or break your performance of your castings at a later date. In casting foundry, normally we don't take the temperature beyond 750 degrees centigrade. Most of the time we try to keep it below 720 in the melting stage. So therefore, the silicon, even if it is not dissolved properly, the chance of getting dissolved here is practically nil. Therefore, we should insist on the alloy supplier to supply an alloy with the fully dissolved silicon. This you can see it only by microstructure. Take a small sample, polish it with a student microscope, which we all used in the schools and colleges. We can have a visual look with 0.5 HF, hydrofluoric acid. You etch it, and then you can see visually. If the silicon appears in the form of needle, it's okay, acceptable. If it looks like a globular or a rounded particles, it is much better. But if you find crystalline silicon, flaky silicon, even at 100 it will be very clearly visible. At 100 magnification, if you see cuboids, this is going to harm your casting at a later stage. When you are using a fully automated machine, highly very sophisticated tools, the silicon particles, being hard particles, will break the tool tip. The wear and tear of the tool at the time of machining will be very high. Therefore, any alloy maker should take care to see that silicon is dissolved completely. Right? There are two things are involved. If the silicon is not dissolved completely, it will keep floating on the surface. It will go into the oxide. You are paying money and buying silicon, and while alloying, if you lose some quantity, it is no use. To achieve 12% or say 11.5%, you add 0.5% more, then you are losing money. And the second also, if the silicon does not go into solution properly, if you have a cubes or cuboids or flaky silicon, it is going to spoil your tool. Not only the machining tool, if suppose you are in, let us say, pressure die casting, you are injecting the metal at a very high velocity. In a very short time, you are trying to fill the casting. So the hard particles, the silicon particles at 680, 690 degrees centigrade, they already will be in the form of a particle. They will, spoil the surface of the gate area. It will create scratches. It will damage. The life of the dies will come down. If you have a very good metal, the life of the die also will go up. So this is why I am coming back to the eutectic point. Let me take you back a little bit. Here what happens, if you exceed 12%, the silicon present is no longer in the form of alpha. It is in the form of silicon itself. Below 12, it is alpha and aluminium. alpha particles of silicon. They are highly dissolved, rounded or needle-like. Whereas the silicon particle itself will be in the form of a flakes or cubes or cuboids, which you can visually see. Sometimes when you break the ingot, the breaking itself will show you very rough surface. I'm talking about incoming ingots from the alloy supplier. Now that is why I always say the dissolving silicon beyond 12% also is very difficult. You have to maintain a very high temperature. Beyond 810, 820, 830, your melting loss will go up. So the alloy maker tends to keep the temperature and silicon solution in a balanced level, so that it doesn't spend too much on fuel. At the same time, ensure that the silicon goes into solution properly. You have to give, say for example, if you are making a 1 ton or 1.5 ton aluminum alloy in the conventional rotary furnace or scalar furnaces, you have to give some time, 30 minutes, 35 minutes. If you are going to do an induction furnace, it's slightly different. Where there is a naturally electrically induced rotary motion of the metal is available, which stirs the metal, and it ensures a proper solution, where silicon goes into solution properly. Whereas in the conventional scalar furnace or rotary furnaces, when you make an alloy, the silicon solution going into solution is to be ensured. The operator or the shop floor engineer who is standing near the furnace has to see that the silicon goes into solution properly. That is why I normally recommend, when the customer gives a range of 11 to 13, stick to below 12, stick to 11.5, below effective point, which will help you or ensure that you have only alpha silicon, not pure silicon present in the alloy. And the alloy maker will always tell you, you are going to remelt it anyway, my ingots are going to be remelted. Fine, he is correct. We are remelting it, but we are not going to increase the temperature beyond 750. You require 800 plus to ensure that the silicon goes into solution properly. Okay, so if we are talking about this hypereutectic silicon alloys are beyond about 13%. For example, piston alloy. In piston alloy, if you polish it, you can see the crystal of silicon particles. It gives an extremely high art, and it is very difficult to machine a piston. You require highly sophisticated diamond tip tools, etc., and to get a proper machined surface. This is why they are adding more than 12%, is that we require a very good surface hardness on the pistons, especially in automobile engines. The piston is the one which gets a lot of wear and tear, and therefore it requires extremely good high surface hardness. That is why we add more than 13% silicon. Hypereutectic alloy is very difficult to machine due to high silicon content, but show a very good wear resistance, hence used in pistons. So that's why whenever I suggest that the casting people should visit the alloy maker, or if you are making your alloy in-house, you ensure that the silicon goes into solution properly. If the silicon does not go into solution, it is going to create more problem in the form of shrinkage at the casting level. While cutting and grinding, you'll have rough surface, and your tools also wear and tear very fast. Okay, now coming to the alloying element copper. This is the second major alloying element. I said element. Copper is a metal, whereas silicon is a non-metal. That's why we were telling element earlier. Copper is a metal. Now, copper melting point is much higher, but still at 750 degrees centigrade, copper is added to liquid aluminum. It dissolves like ice going into a lemon juice. The salt which goes into water, it dissolves. When you maintain aluminum around 750 degrees centigrade, you add copper, in the form of small ingots or small piglets or copper wire or a copper scrap. It goes into solution beautifully. It dissolves very well. So therefore, dissolving copper is not a major issue. Even though copper melting point is very high, silicon melting point is also over 1400 degrees centigrade, 1440 or something. Whereas it dissolves in an aluminum which is maintained at 850, 825, 850. Here, if you come, what is the properties of copper? It improves the strength, hardness, machinability, and thermal conductivity. You are all familiar. Copper is a very good conductor of thermal as well as electricity. When you add copper to aluminum, it improves the thermal conductivity property of the alloy. Decreases the castability. Unlike silicon, it reduces the fluidity, and also copper gives rise to problem in corrosion resistance. Mostly we add between 0.5 to 4%. Most of the alloys are between 0.5 to 4%. Very rarely we go above 4.5%. Here LM12. But the problem at very high copper content, the ductility is very low, very brittle material, and the oxidation problem on the surface on electrolytic process, it becomes appear very dark and matty. So therefore, most of the alloys which are used in casting industry, we tend to keep it around 4.5% maximum. Copper also, copper bearing alloys cannot be used for decorative anodic oxidizing casting. Anodic process cannot be employed in copper bearing alloys. This is very difficult. I am showing you the what you call binary diagram of copper, aluminum and copper. You can see the range between 3.5 to say about 5.5. We don't even touch that point. This point is very important. I'll go back to you. This point is very important. So we don't touch it. We should be well below 5, 4.5%, 3.5 to 4.5. I came across an alloy LM11, which is very high strength, very high tensile strength, and elongation beyond 10%. Beyond 10%. Castability is poor. You can do low pressure die casting or even other types of castings. Gravity die casting is also possible. Sand casting is widely used for this particular alloy. Heat treatable. Again, I'll come back to that slightly later. I'll touch on that slightly, but I'm not going to go deep onto this. See, as I told you, there are few elements which go into a solid solution. That is, one solid dissolves in the other solid. You are all familiar. A liquid dissolves a solid. For example, water dissolves kadi namak or sodium chloride crystals. Molten aluminum dissolves copper. Molten aluminum dissolves silicon. Molten aluminum dissolves iron, bolts and nuts. Everything will get dissolved. Whereas this aluminum and copper has got a slightly fantastic property. It also goes into solid solution, in the sense when it is solid, it dissolves the solid copper. This phenomena is used in heat treatment, wherein we raise the temperature above 400 degree, 500, 525, close to this point, just below this point, 510, 520, 525. Even in some places 540, you can go up to 540, where the copper present in the alloy dissolves. The solid does not deform. The casting remains as solid, but the copper inside dissolves. And when you cool down, it precipitates again. By controlled dissolving and reprecipitating the copper, we achieve a extremely high tensile strength and also very good elongation. This phenomena is known as widely used in heat treatment. Silicon does not have this property, whereas copper has got it, and magnesium. Now coming to magnesium, normally it is added between 0.25 to 0.5%, improves the hardenability by heat treatment. By here also same thing happens. I'll show you the what do you call yeah, you can see aluminum, silicon, magnesium phase diagram. I'll come back to it slightly later again. What happens, magnesium also has got the same property like copper. When heated above 400 degrees centigrade, the magnesium in the what you call grain structure, grain phase dissolves inside the aluminum structure, and then it reprecipitates while controlled cooling and other process in heat treatment. This improves the hardenability. We are all most widely used alloys are LM25, where the silicon is about 6 to 7.5%, and magnesium is about 0.3 to 0.5. Right? It improves the hardenability. Here I would like to say something a little bit. Many people are using LM25 in gravity. See, the entire lecture I prepared it for a classroom session. Here I am not able to see you guys, and therefore I am finding it difficult to explain also. I don't have a drawing board where I can draw and show you. Anyway, coming back to here is that here I mentioned 0.25 to 0.5, right? In LM25, many people are using heat treatment furnace to improve the hardness. Hardness of about 95 to 110 BHN is required for getting a very good machined surface in LM25 castings. Make it, let us say, cylinder heads. Cylinder heads made of LM25, you require a hardness of 95 to 110. Now, if the magnesium drops below 0.3, you will find it difficult to achieve a hardness of 90. Whatever you do in the heat treatment, not possible. Therefore, I always tell the people, maintain magnesium above 0.3, above 0.35. In, for example, a gravity die caster or a low pressure die caster, wherein the molten metal is held over the entire period of 8 hours. For the entire period of 8 hours, you continuously cast it, right? You don't exhaust the metal. What happens here is that the magnesium slowly evaporates at the temperature of 720, 725, the temperature used for gravity die casting and low pressure die casting. The magnesium evaporates. The loss of magnesium is to the tune of 0.05 per shift, roughly. I checked it up at the start of the shift. At the end of the shift, there is a drop in magnesium. So therefore, we should start with 0.35 or 0.4 in GDC and LPDC to achieve a very good hardness at the later stage in the heat treatment furnace. This is very important. You maintain the magnesium above 0.3 in the casting, not in the molten metal. In the casting, we should have a more than 0.3%. Then only you will get a hardness of 95 to 110 BHN comfortably, easily. 0.5 to 1.5 improves the wear resistance and strength. Again, 1.5% used in pistons, cylinder blocks, cylinder heads, and wheels. 3 to 6% only in low silicon alloys improves anodizing properties. Gives a very bright surface finish, decorative parts. These are all more towards the non-automotive components. Again, back to alloying. Due to low potential difference between Mg and Al, corrosion resistance to alkali and seawater is very high. Therefore, use of magnesium in chemical industry, shipbuilding, and food industry is recommended. Magnesium bearing alloys. Grades of magnesium as primary alloying consumed is ideal for decorative appliances. You see, there are some alloys where the magnesium is about 5-6%. These are mainly used for decorative parts where you can very good colors and very good surface finish. Yeah, we are coming to the same again, aluminum, silicon, magnesium phase diagram. When you add a magnesium to, let us say, LM9 or LM6, where you are already having about 11.5% silicon. Again, let me repeat, keep the silicon below 12. 11.5% silicon. You add a little bit of magnesium. We always have only alpha Mg2Si and S. Si is the above 12, above this one, above 0.4. What happens is that the silicon also precipitates in the different form. We require a alpha part. Here, as I explained to you earlier, this also goes into solid solution. Suppose you have a 0.3 or let us say 3%. You are somewhere here. If when you heat it around 520, 530, the magnesium disappears completely. And then when the temperature is cooled, when the temperature slowly comes down, magnesium reappears in the finer form and improving the hardness and tensile strength. So therefore, the magnesium below 0.1, no use. Magnesium has to be above 0.25. It should be around 0.3 to 0.4. Highly recommended is 0.35 to 0.45. Coming back to alloy, iron. Iron is not a alloying element per se. I repeat, iron is not a alloying element per se. Aluminium has got a high affinity to iron. Molten aluminium literally eats iron, whether it is a spoon or ladle or skimmers or dross removers, it just will dissolve in molten aluminium. So we have to have a proper care while using steel spoons or steel skimmers. It should be properly coated with oxide so that the metallic surface does not come into contact with the molten metal. Now, even if you go to the smelter where the pure aluminum is produced, they have a major what you call impurity is iron. So iron has got a aluminum has got a high affinity for iron, right? Beyond 0.5% iron reduces the castability. So we normally recommend iron below 0.4. For low pressure and gravity, ensure that iron is below 0.4. Especially for gravity and low pressure, where the metal is held for more than 6 hours, 8 hours inside the crucible. There, the problem is iron pickup will be more. If you measure the iron at the beginning of the shift and the end of the shift, you will see that there is a marginal increase in iron. Iron once get into the molten metal, it is difficult to remove it. Reduction is impossible. Removal is impossible. Reduction is possible only by dilution. There are some castings, especially wheels, which are made in gravity die casting, GDC process, and here we maintain GDC 70%, 30% by LPDC. Here we maintain iron less than 0.1 because the more the iron, your elongation goes down. The safety critical components like brake parts or wheels should have a very good elongation. This is very important, very critical. It is for the safety of the car, the occupants of the car. If there is any crash, wheel will not break. Wheel will collapse, bend, distort, but it will not break because it has got a very high elongation properties. So that to ensure that the elongation is high, we have to maintain iron below 0.1% in these alloys producing safety critical components. right? In many alloys where you require a higher elongation percentage, try to reduce the iron even below 0.2. Normally we recommend below 0.4 for the commercial grade castings in GDC and LPDC. The problem is come to PDC, where the dies are steel dies, and you all know that aluminum alloy has got a very great affinity, a liking for the steel. Therefore, it tends to stick, चिपक जाता है. There, what we do is that the normal practice is to maintain the iron around 1%, so that releasing is extremely good. But the problem is at 1% iron, your elongation is down to nothing. Casting becomes highly brittle, highly this one. So therefore, we tend to keep the tendency to keep the iron at that percentage is no longer permissible. In the 5-6 years back, even 7 years back, they don't mind 1% iron. But nowadays, no. We have to keep it 0.7 or even below. With the 0.7% iron, it is very difficult to release the casting. So therefore, we have to improve the die coating, the die spray to release the casting. Don't add iron for releasing. You are adding only a material which is very cheap. You are reducing the cost of the alloy. At the same time, you are incurring a problem of the casting, which becomes more brittle. Most of the process uses less than 0.5%. High iron decreases the ductility and machinability. Machinability also gets reduced, and it is very difficult to get rid of. As I told you, you can only dilute it. You can't reduce iron. Once iron gets into the molten metal, casting, molten metal or in the casting, even on remelting, you can only dilute with a better metal with a low iron, so that total iron content comes down. It is very difficult to remove as such. If you have any problem of ejection, try to improve the die spray. Control the die temperature in pressure die casting. Control the die temperature. Improve the spray. Reduce the water. Use a slightly highly concentrated dilute and release the casting. Don't expect iron to be added and produce the casting. Your castings will be very difficult for machining, and also the life of the casting will go down. Manganese in aluminum alloy. This manganese improves the strength and casting soundness. It is normally used below 0.5%. Definitely not above 0.7. We normally recommend half of iron. Suppose the iron is 0.7 or 0.8, I recommend 0.4% iron. Because this controls the effect of iron. This controls the effect of iron on the silicon present. You see, iron always plays its part, spoil sport, in the silicon structure. So there, manganese controls the iron. It ties down the iron. For example, if you have a 0.8 or 0.9% iron, you wanted to control it, add 0.4% manganese. It ties down the free iron which goes after the silicon particles or silicon in the main alloy. So therefore, manganese is used as not exactly, it's a minor alloying element to control the bad effects of iron. Nickel added up to 2% in hypereutectic alloy, aluminum silica alloy, to improve hardness, strength at elevated temperature. High temperature strength is achieved by adding 2% nickel. Very important in case of pistons for IC engines. Zinc. Again, zinc is not a alloy element, but it is added sometimes. Most of the American specification, if you see, you will find some amount of zinc. Whereas European and Indian specs, normally we don't add zinc deliberately. When present along with copper and magnesium, it adds greatly to improve the properties. For example, if the magnesium is in the border range of 0.3, 0.35, presence of zinc helps you to improve the hardness. So therefore, zinc to some extent improves the heat treatment properties. Fluidity improves, but zinc also has got a negative problem. Shrinkage problem may occur. Microporosity, macro shrinkage may occur. LM24, okay, mostly used in PDC. Lead. Again, these are all, I would rather put it in impurity or minor elements, mostly between 0.03 to 1.1%. When between 0.15 to 0.3, it deliberately added, it improves the machinability, right? But we keep it below 0.1% to improve the harmful effects on the environment at a later stage when the material is scrapped. Titanium, per se it is not an alloying element, but it improves along with the combination of boron at the ratio of 5:1, 5 parts of titanium and 1 part of boron. It improves the grain structure. It improves, smaller the grain, higher is the strength. So therefore it improves the grain structure vastly. So we recommend titanium in most of the alloys between 0.1 to 0.15. In some cases, you go up to 0.2% titanium. In some cases, where you require very high strength, high elongation, we go for 0.2% titanium, and normally we don't exceed. This is mainly used as a grain refiner. Gentlemen, you are all familiar with grain refining. Okay, we can touch this subject at a later date. Grain refining and modification. Coming back to strontium. Earlier we used to use sodium as a modification agent 15, 20, 25 years back. It has got its own bad environment effect and all. Slowly the usage of sodium has gone down. Strontium has replaced it. Strontium essentially modifies the way silicon dissolves and appears in the microstructure. Silicon in the form of noodles and silicon in the form of globular structure, rounded edges, right, gives higher strength, higher surface. Therefore, the strontium does a very good job in this area. 0.008 to 0.04% of strontium modifies the silicon structure. So therefore, in GDC and LPDC, where you require a good modification, instead of sodium, we go for strontium. Sodium is no longer used. Strontium also is added in the form of master alloy or small piglets and in the holding furnace. We can also tell the alloy maker to add this strontium and supply to you when he supplies the ingots. On remelting, if it is sodium modified, remelting sodium is lost. Whereas strontium, we don't lose it actually. And the modification effect still remains. At a higher strontium level, casting porosity may occur in slow cooling or thick areas. So therefore, we don't recommend. Gentlemen, there is a very interesting point. I attended one of the seminar done by the North American Die Casting Association, wherein they have done a lot of exercise on this strontium for pressure die casting. Let me repeat, pressure die casting. Even in PDC alloys, you add a small quantity of strontium, let us say 0.01%. I don't remember the exact numbers. I can look into my notes and come back to you at a later date. In case somebody is interested, I can always tell you. This addition of strontium helps very we can have a very good ejection properties of PDC components at 0.7% iron with 0.01% strontium. It improves the removability from the casting. It reduces the affinity of the casting to stick to the die. It doesn't allow the casting to stick to the die. 0.01% of strontium, if I remember correctly. I have to go through my notes again and come back. So therefore, even in PDC alloys, you can drop the iron below 0.8%, keep strontium, a small quantity, it will give you same very good effect in releasing the casting from the die. Gentlemen, before I close this, I also would like to mention about some of the impurities present in the aluminum alloys. We talked about this 1 minute. I didn't mention this again. Okay. Coming back here, if you see the minor elements, we mentioned iron, manganese, nickel, zinc. We discussed about zinc. We didn't discuss about. We discussed about lead also. Tin. Tin is a funny material. This comes into the alloy. It is not supposed to be present, right? It comes into the alloy from the alloy maker. He collects all sorts of scrap from the market, puts it in the furnace and melts it to get this metal. Sometimes tin comes into aluminum scrap and gets dissolved. Now tin has got a very bad effect. The tin combined with high iron content, let's say 0.8% to 1% iron, the casting becomes very brittle. In pressure die casting, this was one of my personal experience. For some reason, this tin content went up, and 1 second. The tin content went up. The casting became very brittle. While ejecting, castings were cracking. It was very difficult to remove from the die. They kept on adjusting the die, polishing the dies and everything. Castings still were cracking. And while handling it and while fettling it, we were losing more castings. Then later we found out it was tin which is the culprit with the high iron. 1.1% iron and a little bit of tin was present. So therefore, whenever you buy the alloy from alloy maker and you do your spectrovac, we normally focus on major elements. Please focus on minor elements also, and also try to make it as low as possible, commercially as well as technically. Gentlemen, thank you very much. And if there are any questions, I will take it. Actually, as I explained to you earlier, I had prepared this mainly keeping in mind about actually this was prepared for classroom lecture, so I was trying to do it by Zoom. I'm not sure how effectively I conveyed my ideas and thinking to you all. Thank you for listening. Questions?
Yeah, thank you. So I think the questions have started coming in the chat box. I also request the other participants to type their questions in the chat box. We have a question from Mr. Patil. What is the importance of sludge factor in production of cylinder blocks in high pressure die casting?
Can you repeat, madam? I can't.
What is the importance of sludge factor in production of
Flux factor.
yes, of cylinder blocks in HPDC?
I request the gentleman to write to me or email the question to Alucard's office. At the moment, I have this one. No idea. Yes, madam. Next question is there.
Yes. Yeah. Just is strontium modifier recommended for HPDC process?
Yes, I talked to you on in length about this. Yes, we do recommend. It will you can go down on the iron content of the metal. You can stick to 0.6, 0.7%. Still make a very good casting, which doesn't stick to the die. And we recommend only for that purpose. Yes, I recommend.
Okay, the next question is from Mr. Sachin Kumbhar. What effect will what will be the effect of silicon is more than 12%?
See, I touch this point again. If it is more than 12%, alloy maker will find it difficult to dissolve in the first place. Second, if it is again more than 12%, anything beyond the eutectic point 11.7, silicon dissolves in the molten metal, but the when you put it in the form of ingots or make a casting, the silicon comes back as a crystal form. This crystals forms a hard particle and your tooltip will get spoiled. And if these particles are more, while injecting the metal into the die, it will corrode the surface of the die. So therefore, silicon, we want it in the form of a needle or a globular or a rounded form, modified form. That is why again we recommend strontium. So therefore, maintain silicon below 11.7, below eutectic point, which is easy to dissolve. At the same time, it will go into full, completely dissolve. It won't precipitate in the form of crystals when it cools down. Next question, madam.
Okay, the next question is from Parth Dhuri. Can you please explain the necessity of higher percentage of iron, I believe, in PDC alloys?
Beg your pardon, repeat please.
Uh, can you please explain the necessity of higher percentage of Fe in PDC alloys?
Well, I'm talking about reducing it. Earlier, about say 7 years or 8 years back or 10 years back, we used to have 1.1% iron. Nowadays, we are reducing it to 0.6, 0.7, 0.8 in PDC itself. The idea is that to improve the strength of the casting, right? Machinability. So iron plays what you call spoil sport in the solidification characteristics of silicon. So therefore, iron we should maintain it lower. To get a good release, you try to add a little bit of strontium. Improve your die temperature. Maintain your die temperature properly. Improve the what you call die lubricant. That is more useful than this. Next question, madam.
Okay, the next question is from Mr. Jeevan Singh. How SNTI in alloy work in modifier?
Titanium in?
SN, titanium.
SN is tin, yeah, correct.
Yeah.
Titanium, I'll tell you, titanium is used as a grain refiner, not as a modifier to start with, right? And we recommend titanium in GDC and LPDC around 0.1 to 0.15. 0.5 is 0.5 to 0.15. 0.05 to 0.15. That is more correct. And in field castings, we go up to 0.2%. That's the titanium. Tin, no. Tin is impurity.
Okay. There's a request from Mr. Vinay Munshi. He says, sir, please explain aluminium silicon phase diagram once again.
You want me to do it now or? Well, I don't mind doing it. You want me to go back? I explained 2-3 times. So let's see. If in
Okay.
follow-up lecture, I will.
There's other questions and maybe we can come back to it.
Yeah.
Yeah, there is a question from Mr. Jitendra Parekh to you. How to achieve elongation at 2% in LM25 alloy? Iron percentage at 0.5, copper 0.2%. please suggest T6 cycle temperature range for solution and aging.
Okay, beautiful question. Very interesting question. Please maintain the iron not at 0.5. Reduce it. The moment you reduce the iron, elongation will go automatically up. Okay, the elongation will go automatically up. Don't go for 0.5% iron. No. Right? Talk to the alloy maker. Ask him to give you less than 0.3. Your own recycling of runner, riser, gates and all will be there. So the iron is bound to go up. So therefore, tell the alloy maker to supply the metal below 0.3. It may be slightly more expensive, but it will save you a lot of money at heat treatment, and subsequently customer rejection will be very, very, very minimal or practically zero. Therefore, you maintain a iron as low as possible, your elongation will go up. I would recommend 525 degrees centigrade for solution treatment, and precipitation 180, 185, 190, 200 precipitation. But ensure that magnesium is above 0.3 and iron is as low as your commercial people can allow you. It's a balance between cost and benefits. Yes, madam, next.
Okay, the next question is from Vishal Suryavanshi. In ADC 12 alloy, is any element can any element cause soldering defect in HPT?
See, soldering defect normally occurs due to various reasons: improper dye lubricant, dye temperature, high dye temperature, etc., etc. Assuming that all the other factors are controlled, higher iron will reduce this building or the sticking problem. So therefore, we tend to increase the iron content, but don't do that. I recommend a little bit of strontium will help you to release the casting and also reduce the sticking tendency or soldering tendency.
Okay, there's another question. If we are melting alloy more times, then which elements will get affected and by how much percentage?
Beautiful,
Question
beautiful.
by Vijay Jangam.
So very good, very interesting. Theoretically or technically, aluminum alloys can be recycled any number of times without losing any properties, right? But the problem is that magnesium, on remelting, you lose, especially if you increase the molten metal temperature beyond 725, 750, 760 degrees centigrade, you tend to lose magnesium. So you have to add magnesium. Okay, on remelting. And whenever each time you remelt, some or the other, from somewhere the other, iron gets picked up. So therefore, iron also will go up. The remelting, we have to take care to see that there is no iron contamination. For example, while cutting the runners and risers, there will be some iron powders mixed along with the turnings and borings. Machine shop aluminum scrap will have iron turning, steel turnings. So this should be completely removed. You put through magnet couple of times and remove all the iron particles. Iron particles should not be there. The skimmers, the launders, the spoons, everything should be coated with oxide coating, which prevents aluminum coming into contact with the steel surface. So iron pickup should be reduced on remelting, and the tendency of magnesium is going to go down. So therefore, you add magnesium. When it is ready for pouring, you add a little bit of magnesium. But nowadays with Spectrovac, you can check the magnesium very quickly and add a little bit in the form of master alloys. I think I have answered your question. Still, if you people have any doubts, please write to Secretariat and they will pass the question on to me. I will try to reply as much as possible.
Yes. There is a question from Mr. Yashwant. For cylinder head heat treatment, what should be solutionizing temperature?
I can go up to 540 if you are sure of metal composition. If you are very good in controlling the metal composition, you can go up to 540, but I recommend 525. When you are going at 540, your furnace should be top class. Your temperature control inside the furnace should be very good quality, very high quality. Even if one zone by mistake increases in temperature, you will have a catastrophe, disaster. So therefore, I would recommend 525 to 540. 525 is good enough, but control the metal composition. Repeat, control the metal composition. Keep the iron low. Keep the magnesium above 0.3, 0.35. You will get a very good problem, very good results.
Yeah. The next question is from Mr. Daniel Franklin. He is asking you, which element helps in reducing shrinkage?
Well, frankly, to some extent modification, to some extent titanium boron addition reduces the shrinkage, but this is something which you cannot help it. There is a volumetric shrinkage between 3 to 4% in aluminum alloys. You have to compensate it by die design in LPDC, PDC, LPDC and GDC. You have to control it by providing sufficient riser and proper runners. Proper head has to be provided. This has to be taken care of at design stage as much as possible. I can quote a small funny part of it. If you degas too much, you'll have more shrinkage. If you allow a little bit of gas in the molten metal, when it solidifies, the tiny gas particles which get entrapped, they expand and reduce the shrinkage. But you will have gas porosity. It's what you call, you have to balance in between. If the castings, you don't require a very high strength. The castings where you don't require a high tensile strength or elongation, you can fool around with reduced degassing. But there is no question of improving the shrinkage by adding element. No. One thing is that if silicon goes into solution at the alloying stage properly, you will have less shrinkage possibly.
Okay,
Next question, madam.
Yeah, the next question is from Mr. Damodar. How to improve molten metal homogeneity probably? Which element helps in reducing shrinkage? Same thing. I think the question.
Yeah, I think I repeated part of it. The part of is that homogeneity. Well, induction furnace to start with, it has got a small stirring action, electromagnetic stirring action, which improves the homogeneity. I agree. High silicon, what do you call, alloys tend to have a segregation. So you have to keep stirring the metal. This top portion will have lower silicon and bottom portion of the crucible will go up in silicon percentage. So that is why normally below 11%, this homogeneity doesn't occur. Homogeneity has to be maintained at the alloying stage. Once it is done there, you won't have much of a problem in the foundry or casting stage. So what I recommend is that tell the alloy maker, I want homogeneous metal. Take an ingot supplied, take a microstructure, have a look at it, then take a call. So therefore, I would recommend more focus on alloying stage and on as far as possible, try to, you melt the alloy, clean the alloy, degas the metal. Yeah, degassing also will improve the homogeneity. Nitrogen bubbling will also improve the homogeneity. Next question, madam.
Yeah, the next question is from Mr. BK Srinivas Rao. What is the recommended ratio of pure metal and ingots or razors if we are mixing them?
Well, in which process? If it is GDC or LPDC, 80-20 or 65-35, 60-40 or 80-20, depending on the criticality of the casting. See, some dies, some castings are finicky and they are very careful about the metal. Some are can take any damn metal, still produce a good casting. So therefore, it depends on the casting, casting to casting. Normally, we recommend 70-30. 70% virgin alloy, 30% recycled runner and riser. Again, it depends on your die design and all. Suppose you have a casting where the yield is only 50% or 40% was sand casting or GDC or what happens? There 40% runner riser. You are already having 60-40, and there are on top of it some 5 to 7% rejected castings. So this happens, but general recommendation 70-30.
Okay. The next question is from Mr. Jitendra Parekh. How much SR to maintain in LPDC GDC process if the casting wall thickness is between 5 to 10 mm to prevent porosity?
What to maintain? What exactly? Repeat, please.
How much SR? That is what he has said. SR.
Strontium. Okay. Strontium. I'm not able to recall the number right now. Please send me an email. I will reply to you. If I remember correctly, 0.015. Yeah, if I remember correctly. But I need to check. Incidentally, Alucast Secretariat has produced a handbook, what we call technical reference handbook. Whatever I talked today, many information is there in that book. And it's a reference book. I won't say it is a textbook. It's a reference book. You can all go through it. You can write to our secretary. She will send it across to you. Yes, madam. Next question.
Yeah, the next question is from Mr. Sunil Godse. Which aluminium alloying element is recommended where microporosity should be minimum after machining?
Microporosity is mainly due to gas. You have to do a thorough degassing. Thorough means thorough degassing. And you measure the density index before taking up for what you call pouring or casting. So density index instruments are available nowadays in the market. You measure the density, right? Higher the hydrogen content, the density will go down. Higher the density, you will have an excellent, very little microporosity. Normally, we recommend density index less than 1.5 for LPDC and GDC, where porosity should be very, very low. PDC, we can go up to 0.4. 4%. 4. 1 to 1.5% is allowed for GDC. Density index. You require a density index, you have to check. Thorough degassing is required. Next question, madam.
The next question is from Mr. Vijay Jangam. He is asking whether the HPDC parts need heat treatment, because some parts like filter that customer needs heat treated. So is it applicable or not?
Yeah, definitely. HPDC parts can be heat treated provided you cast it with a vacuum technology. You remove the air entrapped in the die before the metal gets into it. So vacuum technology is widely used nowadays in almost many foundries across India. If you are having a vacuum die cast, vacuum attachment along with the die, if it is there, you can heat treat those castings highly effectively, because what happens is that in heat treatment at the temperature of say 500 degrees centigrade or 525 degrees centigrade, the hydrogen bubble, a tiny bubble inside, right? The pressure will be around 400 atmosphere in pressure die casting. When you inject the metal, there's a gas bubble gets trapped. If you put it in the heat treatment furnace at 520 degree, it will literally explode. There will be a minor explosion. It will appear as a blistered surface. It will blow out of the casting. So therefore, either thoroughly degas or go for vacuum application. It is recommended. Yes, we can do it.
The next question, how to maintain density index of aluminium alloy consistently? Which factors do we need to follow?
Well, I recommend that after degassing the metal thoroughly, check for the density index, right? Before degassing and after degassing, you yourself will come to know it very easily, very quickly. No problem. That parameters you have to maintain, how much you can allow. It's very easy, not difficult, and the instruments are available widely now.
Okay, then there is a question, what can be the effect on a casting process if we use ingots with visual porosity LM6? This is a question from Mr. Dinkaran.
This is always what you call uh, uh, we can argue either way, this way or that way. On remelting, the visual porosity will go on down. I don't accept it. As a metallurgist, as a production engineer, if the ingot has got porosity, that means it has got hydrogen, entrapped hydrogen, right? On remelting, the hydrogen again will go into solution. It will dissolve. It won't come out. So therefore, you have to degas more. So I recommend, tell the alloy maker to degas the metal and then supply to you. So therefore, he has already reduced the hydrogen. On remelting, whatever little bit hydrogen you pick up in your shop floor, you have to degas it. If the alloy maker does not do proper degassing, you have to do more. So therefore, it is a discussion between you and the alloy maker. Insist that alloy maker should supply the ingots on degassed condition. Simple. Visual porosity, personally don't accept. That's my recommendation. Again, it's a cost versus commercial versus technical requirement balancing act. Yes, madam, next question.
The next question is again from Mr. Jitendra Parekh. He is asking if we are achieving desired mechanical properties in less solutionizing time, that is say 2 to 4 hours, then can there be any bad impact on casting quality due to less solutionizing time?
No, not at all. Not at all. In fact, the castings which are thin, which are not heavy, thin walled castings, and all we can solutionize temperature can be brought down to 3-4 hours. It depends on the thickness of the casting. If you have 15 millimeter thick casting or 10 millimeter thick casting or cylinder head or cylinder block, I would rather don't take a chance and go to 8 hours. If the components are small, the components are thin, you can definitely reduce the time. Solution temperature time, solutionizing time, as soon as it reaches the solution temperature, not from the starting point. The moment it reaches the solution temperature, we can cut off at 3 to 4 hours, no problem. It depends on the component to component, casting to casting. Cylinder block and cylinder heads, which are more bigger, bulkier, and there are a lot of internal passages are there. So therefore, we tend to go slightly higher. We want a homogeneity in temperature across the casting. Surface may reach 525, but interior may not have reached 480, 490. So therefore, we are asking you to maintain 6 to 8 hours, 8 hours at that temperature, so that across the casting, every portion of the casting, inside, outside, interiors, reach homogeneous temperatures.
Okay, the next question is again from Mr. Dinakaran. Which element will solve the porosity or pinhole in GDC?
I repeatedly told you degassing. Degassing will reduce the pinhole porosity.
Okay.
It's not going to be much of an element. Some element do cause porosity to a better extent. For example, silicon not properly dissolved will cause porosity. If you ensure that silicon goes into solution properly, you will have less porosity, right? But less shrinkage, less porosity. But if you wanted to control porosity, main hydrogen, go for density index machine. Check the density. Remove the gas. Yes, madam. Next.
For alloy wheel, how much pouring temperature should be set?
Well, it depends. I would rather look at the casting, look at the component and all. But normally we don't recommend 10 or 20 degree more than the required. Say 700, 710 maximum. But again, it depends on the die design, how the pouring is done, how the metal is lifted, how it is brought down and done. So these things have to be looked into it before answering the question.
Okay. There is a question, I think, which has come again twice from Mr. Dhananjay Kumar. Beracketing of aluminium can dissolve directly in holding furnace of tower furnace. This is the statement he has made.
You can remelt anywhere. That's not an issue. You can remelt the scrap casting in the holding furnace, or you can put it in tower furnace. That's not an issue. But I don't understand the question in the first place. And the meaning is that when you are running a GDC operation, if keep on adding one piece or two pieces into the furnace, right, the temperature keeps fluctuating. All the castings which are produced are not at the same temperature. So therefore, I would rather don't do this for especially critical or important castings.
Okay. So there is a question from Rockman Industries. Sir, how to reduce the hot spot in the casting?
I have to think about it. Hot spots. I don't know. Could you kindly send me a question, whether it is GDC or PDC or LPDC? And if you possible, send me a photograph of the casting. Send it to our secretariat or Kirti madam. I will answer the question.
Yes, sir. Now, he's asking about HPDC, sir. The question that has come from Rockman.
Okay.
This is in the context of high pressure die casting.
Yeah, then I will look into it. Kindly send me the detail. Thank you.
Okay. How to identify the primary ingot quality except chemical composition? Question from Mr. Dinakar.
Chemical composition, you do spectrovac or a chemical laboratory, they will get you the analysis. I would recommend personally break it. Macro. Just take a ingot, break it into two, hammer it, and break it into two. See macro. The macro structure should be fine. You can visually see if it is a fine grained structure, you will have less problem on remelting and recasting. If it is coarse grained structure, you will have a problem. So this is known as macro examination of incoming ingots. The second is micro. Micro is take a small piece from somewhere of the ingot, cut it into half, again cut it into half, take a small piece, 10 mm by 10 mm by 10 mm, polish it nicely, machine it, polish it nicely, put it under student microscope. You can etch it with 0.5 HF, and then you can see the structure. Structure will look very beautiful. You can look at it and you yourself can take a decision. If you find crystallized silicon particles, then catch hold of your alloy maker. He has not done a good job. The particles should be fine. There should not be any segregation. There should not be any cluster formation. These are the things we have to check. That's all. Well distributed. As 1,000 rupees, may not be 1,000. Student microscope is good enough.
Okay. There is a question again from Mr. Parekh that if magnesium percentage in LM25 alloy is increased up to 1.2% instead of 0.5% in regular practice, what can be the bad effect on the casting properties after the heat treatment?
I have no idea, madam. 1.5%, I have absolutely no idea. We normally recommend between 0.35 to 0.55. 1.5%, there are very few alloys we have that kind of concentration level. I have no idea.
Okay. Is there any process to reduce excess zinc percentage from molten alloys? Again, a question from Mr. Parekh.
Yeah, no, dilution. You buy a fresh metal with lower zinc, add it. That's the only way. And zinc again, In American speak, they go up to 1%. Okay, I would rather recommend as low as possible, 0.1, 0.2. It's okay. But dilution, only magnesium can be removed if you want to remove magnesium. Where suppose you have some alloy where you don't want any magnesium. There's one alloy where you want zero magnesium. We can add sodium silicofluoride, which will kill the magnesium completely. DMAG, magnesium removal is possible.
Okay. There's a question from Mr. Vasudevan. Holding cum melting furnace. What should be the metal temperature?
Holding cum melting, that itself makes a lot of sense. Well, we require casting pouring temperature plus 510 degree more. If you can hold it in holding cum melting furnace, you can do that. You are talking about furnace temperature or the metal temperature? I am not able to take it here. But if it is furnace temperature, then try to keep it as low as possible. There is no hard and fast recommendation. It depends on the pouring temperature.
Okay. There's a question from Mr. BK Srinivas Rao. Sir, we have customer returns aluminum components with high oxidized. If we melt them, what is the process defect that will come, or it won't have any effect? This is what.
Well, normally there won't be any effects on the property of the metal which is coming out, molten metal which is coming out. But oxidized casting, you will have more melting loss. Metal loss or melting loss will be there. You may put 2 kg of casting, you will end up with 1.95 or something like that. The melting loss will be more. Oxidation loss will be more. Oxide will float off. On remelting, oxide will float off. That should not be a major issue on the quality aspect of the molten metal. On cost aspect of it, you are losing metal. If you ton 1 ton of scrap, you are getting it. You may not recover all the 1 ton. You will recover less. That means you are losing money.
Okay. There's a question from Mr. Damodhar Priyan. Which elements lead to increasing inclusion?
Leads to inclusion. Well, nowadays we normally go for filtration of metal and all. A lot of technology has come into the market, but inclusion as such, I don't. Inclusion should not be there in the first place. Material should not, oxide particles or crucible pieces should not come into the casting at all in the first place. But any metal can have this problem. Any alloy can have this problem. You have to go for filtration of the metal at the time of pouring, or they use wire mesh for filtering the molten metal in LPDC and wheel casting and all. This is widely used. Recommended is procedure is filtering, but element doesn't play much of a part. If at all there is some problem, if the silicon does not go into solution properly, you may end up into inclusion or segregation. That is possible.
Okay. There is a question from Mr. Vijay Jangam. We have observed microporosity after machining for LM4 material of GDC process. So how do we control it?
Microporosity, again going back, hydrogen. Please remove hydrogen, degas, 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 nitrogen, bubbling, density index. Same answer. Let me repeat again. Degas thoroughly. Check the density index. If it is less than 1.5, go ahead and pouring it. You won't get it.
Okay.
Zero porosity is impossible. But extra quality at the first level, you can get it beautifully with proper degassing.
There is a question from Mr. Dhananjay again. Wire mesh and ceramic mesh, which is better for low pressure die casting?
Well, if you are doing sand casting or a larger casting, a bigger casting by sand, I would go for a ceramic filtration where the filtering efficiency is extremely good, right? If you are using a wire mesh, the problem is that on remelting the runner and riser, the wire mesh bound to come into the molten metal, and the ion pickup will drastically go up. Iron is like a, I don't want it. It's like a salt. It should be controlled. It should not be more. If it is more, then you'll have a problem. So therefore, wire mesh remelting, you have to take extra care.
Okay.
Cheaper. Ceramic filter, costlier, one-time use, throw it up. Both are one-time use. Ceramic filter doesn't have any problem. On remelting it, the filter will float away. Filter will float away and come along with the dross, oxides. So ceramic is costlier, but you have to use it only in a large casting, in a bigger sand casting or a gravity die casting. Yes, you can use it. It's a good one. Better than wire mesh.
Okay. There's a question from Mr. Vishal Suryavanshi. In ADC 12 alloy, can any element cause soldering defect?
I think I discussed this again and again, a number of times.
Okay.
Well, it doesn't cause actually the soldering defect, not due to element at all. It is, see, as I told you, aluminum alloy has got a tendency to steel. They like steel very much. They eat up steel like anything. So therefore, you should have a very good dye temperature, proper dye temperature maintenance, very good dye lubricant, proper spraying system, and dye heating and cooling conditions. The thermal management, I would rather say, that is more important.
Okay. There was a question from Mr. Daniel Franklin. What is the role of iron in elimination of cracks?
Elimination of?
Cracks, cracks, cracks.
Well, to my knowledge, if iron goes up, you will have a cracking tendency. Iron combines with the silicon and makes more brittle material. So therefore, iron should be reduced as low as possible. Cracking tendency also will go down.
Okay, I hope all the questions, like we have tried to address all the questions. Any more question? I don't see any more questions. I have tried my best to scroll through the questions again and again. Mr. Dhananjay, you have a question again? Was this in continuation to the question that you had asked, wire mesh or ceramic mesh? Bracketing can be directly melt in melting furnace holding portion. This is what you have written.
Well, whatever you do, there will be some amount of ion pickup. There will be accidental wire mesh going into the portion, and removal of the. If you take extra care, wire mesh is definitely a good solution. But if it extremely good quality casting where you want very low inclusion, ceramic filter is the answer. You have to strike a balance between the cost and the benefits.
Okay. One more question. I hope, Mr. Dhananjay, you have got an answer to your question. There's a question from Mr. Damodar Priyan. Sir, aluminium alloy, auto degassing for 250 kilogram molten. How many minutes are required?
I would recommend you ask this question to the supplier of the degassing instrument or the machines. They will be able to tell you what should be the pressure of the nitrogen, flow of nitrogen, and then timing, right? Generally, we recommend 15 minutes, 5 to 15 minutes. 100 kg, it's small quantity. 5 minutes is good enough. But this is not the right answer. It depends on the flow of nitrogen, the quality of nitrogen, how many liters per minute you are pumping it in, and how fine the bubbles are. So all these things come into it. If the bubble size is very fine, the quantity is right, the pressure and the temperature is correct, you can go for a reduced time, but minimum 5 minutes. Anyway, the better to ask the question to the supplier of the equipment, and also trial and error. You can do yourself. You can do it 5 minutes. You can do it 3 minutes. Check the density index. Do 5 minutes. Check the density index. Do 10 minutes. Check the density index. You yourself will come to know which one is better. Better the density index, better.
Okay, I see one more question from Mr. Vijay Jangam. If we are having child part and aluminium part assembly and child part having gray cast iron material and aluminium part having LM4, but after solidification, if it is getting shrunk and show blowholes near the child part, so how can we overcome this problem?
This is another very interesting question. Yes, good part. If you are going to put a steel insert or a cast iron insert into a aluminum die and pour the metal, what happens is that the insert also should have the same temperature as the die. Suppose the die temperature is, let's say, 200, 220 or 230 in that area, and the insert you have just placed it hardly 50, 60 degrees centigrade, and you pour the metal, you will have a problem. So the insert also should have the same temperature. So preheat the insert before inserting into the die, cast iron or steel. Preheat the insert, and then you won't have this shrinkage or what you call the inclusion or whatever blowhole problem near the surface. Second, the insert while handling, I would recommend sandblast it or shot blast it. The surface should be free from moisture. Don't touch it with your hand. Don't even leave your thumbprint on it. Pick it up with tongs, put it in. So the surface should be clean, oil free, grease free, because most of the components come from their component manufacturing plant with oil, grease, and all sorts of contamination, kerosene, you name it, it will be there. So you should clean it thoroughly, preheat the insert, and then insert it. Then you will have extremely good bonding.
Okay. I think there were one question probably we missed. Question from Mr. Sachin Kumar. Can silicon reduce the shrinkage and solidification time?
No, silicon actually creates, especially if the silicon is not modified, you will have more shrinkage problem. And regarding timing, not much. There won't be much of a difference. This is my personal view.
I see one more question, or I don't know, like a comment from Mr. Dhananjay Kumar. Aluminium wheel spoke area can be TIG welded. I don't know whether.
Aluminum can be welded.
Yeah.
If there is a density index is extremely good, gas porosity level is extremely low, you can weld it beautifully, no issue. Provided you have a least amount of hydrogen porosity, you can weld it beautifully.
Okay.
Madam,
Yeah, I think we had an exhaustive QA session, and Sir has done his level best to answer all the questions. In case if there are some questions that are unanswered and questions that we have not noticed, please feel free to email these questions to us on the Alucast email ID, and we will see to it that your questions are answered. And I must thank Ganeshan sir for a wonderful and insightful presentation, as well as taking efforts to answer each and every question that was asked during the Q&A session. And I must tell you, sir, that we got an overwhelming response for this particular subject. And I think because of some technical issues, there were some participants who were not able to join. It may be a network problem on their end, but then we have got a request that this session, this training program on this topic be arranged again. People who were not able to attend, because we have got the registrations exceeding our limit. Almost 3.5 times more the what we had expected, and the capacity of the training session was. So a request has come to us that we arrange one more session. So the people who were not able to attend can probably attend the next time. So this is a special request from the ALUCAS Secretariat to Ganeshan sir that please make it convenient to spare your valuable time for us again, so that we have one more session. And like many people are interested, and something very interesting that I found when I scrolled down the list of the participants is like it was not only the fresh engineers who have stepped into die casting, but even senior people from many of the reputed industries also were a part of the participants for this session. And I think some of the participants have been very active and very interactive. That is what we noticed from the questions that were actually pouring in, I would say. Okay. And then we have tried our best. I tried my best to see to it that at least one question of every participant is being addressed. And I'm sorry if I have missed any question. So as I said, if some question remains unaddressed, unanswered, please write to the ALUCAS Secretariat. We will see to it that the response reaches you. Thank you so much, participants, for joining for this webinar. And we look forward to participation from all of you for the next learning sessions that would follow in this month, as well as in all the months in this calendar year to follow. I wish all of you a wonderful transfer of knowledge to your workplace, whatever you have gathered through this wonderful session. And as I said, a very happy transfer of learning. And I hope all of you are safe, and please continue to remain safe. Take good care of yourself. Please do follow all the COVID norms, because the cases even in Pune as well as the other parts of the country, as we get to know from the news channels as well as the newspapers, that the cases are going up. So please take care of yourself, remain safe, remain healthy. Happy New Year once again, and we all hope that 2022 really turns out to be a safe, healthy, and a prosperous year for us. And one more mention before we close for today's webinar. We are very happy to announce that 2 publications have been released in December 2021 from ALUCAS. One is the Directory of Aluminium Casting. The 10th edition has been released. And then the ALUCAS Technical Reference Handbook, the 6th edition has been released. And this is Ganeshan sir mentioned that some of the things which he discussed today in today's webinar, they are a part of this technical reference handbook, and it can be a good reference material for all the die casters. So do feel free to write to us if you are interested in these publications. We will see to it that these publications are sent to you through courier service at the earliest. Thank you so much for joining. Anything more to add, Ganeshan sir?
No, thank you.
Thank you so much, sir. So with your permission, may I close the session?
Thank you.
Yes, thank you, everybody. Thank you very much. So we close the session, and we will meet very soon in the next webinar. The email communication will reach all of you, and will keep on reaching you as and when ALUCAS comes up with any learning and development initiative. Thank you so much.